Okay. Yes, good morning once again, everyone. My name is Lesedi. I'm with the School of Electrical Information Engineering at WITS. I recently joined last year, May. I was previously with CSIR, the Council for Scientific Industrial Research. So I'll be presenting on the effects of the three-level neutral point clamped inverters on the core losses, because most talks are usually on the converter itself, like the power quality and so on. But less work is actually on evaluating what are the effects of inverters now on the core losses of machines. So the machine in particular which we're working on is the Reluctance, Synchronous Reluctance machine. This is part of the my last PhD work. I was supervised by Prague, Pillay. These were some of the students who we co-worked on this work. Okay, so I'll sort of give a motivation why the three-level inverter, and then the test bench, and then the methodology on the losses, on the core loss measurements, the drive itself, and the experimental results. So there's two methods that I'm implementing. There's one method and the other method where you directly connect your inverter to the toroid of the stator. Okay, so the three-level inverter, there's been, in vehicles particularly, there's been a high, even renewables, there's been a demand for high DC bus voltage utilization. In vehicles, the more the voltage, the more the performance. The performance of the vehicle can be improved, acceleration, and so on. However, if you use a conventional two-level inverter, you will have to, a switch would see a very high voltage. So switching from zero to a very high voltage is a huge strain on the switch. And if you look at the dV/dTs, so your variation of dV/dt becomes huge. So your CDVs, your harmonics injections become amplified on a two-level inverter if you are to rise your DC bus voltage. Whereas a three-level inverter allows you to break down the high DC bus voltage into steps. So for a three-level inverter, a switch will literally see a third of the DC bus voltage instead of seeing the whole DC bus voltage. So in terms of components, if you're to buy a switch for a multi-level, you don't have to buy, if your DC bus says 200 volts, you don't have to buy a switch that can withstand 200 volts. You can buy a switch that can withstand a third of that, because that's what it will see. So those are the other advantages with it. However, one of the challenges is the balancing of these two capacitors, these two caps there. Because for you to really enjoy the three-level inverter effect, those two have to be balanced. Because there's another state that it offers you, the zero state voltage. So this is the waveforms. That's your typical two-level inverter waveforms. These are line-to-line voltages. So you can see already with your three-level inverter, it approximates a sinusoidal waveform. So already you can see that on a three-level inverter, you'll actually have low harmonics on your voltage waveforms compared to a three-level inverter. These are experimental results. And so now the question is, what is the effect now of this inverter now on the losses on your machine? So hence the motivation to now look at that. However, currently there's actually not much standards. I don't actually recall. At the time we were doing this, there was actually no standards on how do you do core loss measurements for inverter-fed machines. Most core losses standards are sinusoidally fed machines, but there's not much on pulsed supply onto machines. So the technique we used here is partly inspired by Buglietti, one of the Italian professors. He has a paper where he does a technique to, he's basically trying to propose a standard. So I think in the few years there would be a standard that will come from IEEE for measuring core losses of machines when they are inverter fed. So we used a Simulink D-Space. So that's the setup of the test bench. You have this toroid here. This is the stator of the synchronous reluctance machine. And you use an amplifier. What an amplifier allows you to do is to inject whatever shape of voltage waveform you want. You'll be able to inject it into the core. So that's what it allows us to do. And core loss measurements is really a product of the currents on the primary with the voltage on the secondary. That gives you the losses of the core. It's a standard measure of losses. So it's a 36 slot stator toroid. We had different turns for different frequencies. For example, we can't do 60 hertz for 36 turns. So we increased the turns to 72 turns to be able to go to 60 hertz. Otherwise, you get core saturation. So conventionally, people use an Epstein frame. So with an Epstein frame, you take a lamination, you put it in an Epstein frame, you do your same technique, primary windings, secondary windings, inject voltage, you measure voltage on the primary, current on your secondary, the product of the two gives you your losses. But then the challenge, we find that a bit unrealistic in a way. It's commonly used because once you build your machine, you've actually changed the properties of your material. So our approach, we feel it's closest to reality because we are working on a core that's already has gone through a process of modifying the stator material. So for example, on your finite element tools for machine design and so on, you'll have there the pH loops, core losses of a certain material. But then those are ideal materials. They've not gone through processing. Okay, and then this picture here with the drive, to also sort of bring the work close to reality, is we captured the currents. So we injected the motor, ran it at loaded conditions, then captured the current waveforms. So after the current waveforms, we then inject that into a finite element model to then inject the flux densities into the core. So it's sort of the flux densities that we'll be dealing with actually are coming from the real actual experiment of the machine being run at loaded conditions. So typically, this would be your speed reference. So the angle there is with these synchronous machines, permanent magnet and synchronous reluctance machines, there's usually an optimal angle to run your machine at the maximum torque with the least amount of current injection into the machine. Sort of those are the curves of those experiments where at different currents, the red one is at 4 amps, the maximum peak current at full load for this motor was 16.2 amps. So you can see that you get the least amount of current for that torque at about 60 degrees. So that was the angle that in the experiment we used, and also in a finite element model we used, which there was a correlation, in fact. And this is the experimental setup. So this would be your, this pointer doesn't work well. So this would be your synchronous reluctance machine. That's your 3-level inverter, 4 caps, 2 in series. And we used OPLRT as for real-time simulation. And that's your sensors. And then loading, we used a DC machine to load so that's the first part where we want to extract the current waveforms. And then these are the resistive load for loading. So now this is the current waveform. The top one is the 2-level inverter current waveform. The bottom one is the 3-level inverter waveform. I mean, already you can see some of the spikes are a bit sharper on the 2-level compared to the 3-level inverter. These are phase currents. The motor was in delta, so that's why probably you'll see a third harmonic there. So that's the first part, to extract the current. And then the second part, we inject this current into an FE model of the motor, to extract the flux density waveforms. So we took 2 points, the density forms, the flux density waveforms from the tooth, and the other ones from the yoke of the machine. So this is the, I can't remember if they are tooth or yoke. So this is one of them, and then this will be for the yoke. This will be the tooth. So now, after extraction of the flux density waveforms, we go back now to measure the core losses. So what we do is we inject those flux density waveforms, the tooth ones and the yoke ones, into the yoke of the synchronous reluctance machine. So the amplifier allows us to inject those waveforms, those shapes of the waveforms, into the core, for us to be able to measure the losses for the yoke and for the tooth. As we know, core losses, you have both hysteresis and eddy currents, which form your total core losses of your machine. So we wanted to separate these two, the eddy currents and the... So what you normally do, you measure your total core losses, and then you do it by cycle, by frequency. So for example, we measured at around 20 hertz, and at 30 and at 40. Usually, this measurement should be at low frequencies. And then you extrapolate to the y-axis. Where you cut the y-axis, that is where you get your hysteresis losses. And then from there, those are the eddy currents. So now that we have the hysteresis losses, which would normally be fixed for the per frequency, per hertz, we would now be able to subtract, every time we measure the total core losses, we'll subtract the hysteresis losses for the eddy current losses. So these are the hysteresis losses with different peak flux densities. For example, 1, 1.2, and 1.4, which will be the peak flux densities that we'll be using to measure our core losses at. So the eddy currents, as you can see, you have more loss density for the 2-level inverters compared to the 3-level inverter. 1.2 up to 1.5 Tesla. We had limitation on the hardware itself, because to get more flux densities into this yoke, we need a bigger amplifier. So we had a limitation of the amount of currents we could really inject into this thing. So this is at 3 hertz frequency of the flux density waveforms. And then this is at 60, and then this is at 80. As we know, core losses are a square function of the frequency of the flux density. So in all the results for eddy currents, we're measuring lower losses for the 3-level inverters compared to the 2-level. Well, in summary, the difference for at 30, 60, and 80, the max we got was at 60, which was 11.1 difference percentage between the 2-level and the 3-level. That's for the stator. And then for the yoke, we had 6.9 max in a way for the 3-level inverter had 6.9% lower core losses in these results. And then on the pH loops, you can see the 2-level one is the top one, the 3-level is the bottom. So it has more ripple effects, which means more contribution to the core losses. And those are the minor loops. As you can see, the 2-level inverter has more minor loops inside, whereas the 3-level has only two minor loops. But the 2-level has another minor loop within a minor loop. And of course, that has to do with its inherent higher harmonics as compared to the 2-level inverter. This was at 180 hertz of the fundamental flux, peak flux density. So the other set of the experiment that I spoke about was, we now want to see the effects of switching. How does switching itself, the modulation index and the switching effects, affect the core losses of the core? So we couldn't do that with the previous one, because the previous one we extracted the currents. Of course, on the currents themselves, inherently, there will be traces of the switching effects. But now it's a question of sampling. How well were you sampling this thing to get it into your FED, finite element model, and to be able to really talk about the switching effects. So it was sort of a long shot to argue. So rather, we connected the inverter itself directly to the stator yoke so that we can directly measure the core losses as we vary the switching frequencies and the modulation index. So these are at different flux densities. Again, we see the 3-level inverter has less loss density as compared to the 2-level inverter. And then the effects of switching frequencies. So we plotted the curves along each other for 30 hertz and 60 hertz, 180 of the fundamental flux density waveform. And we can see the y-axis is the modulation index. As you can see, as your modulation index increases, there's sort of a linear relationship between your modulation index and the amount of core losses that you would capture in the machine. So I mean, the 10% or so might not be as significant in large machines, because usually big machines, you are talking above 95, 96% efficiency. But for small machines where your lowest efficiencies are about 85%, a 10% improvement is actually significant. And then these are your BH loops. As you can see, you have more minor loops again, sort of mostly projecting inwards as compared to your 3-level inverter. Again, from there you can see that the indication that the 2-level has actually more core losses as compared to the 2-level. But okay, what does this all mean? This is what sort of a summary of what has been done. But the observation is that there is more loss savings on the stator tooth compared to the yoke. Now, this is very important, especially for induction machines, where cooling or heat dissipation is one of the big challenges. So, and the tooth are the most places which are not easily cooled compared to the yoke, because the yoke you can drill in whatever method of cooling, either air or water or some of those liquids. But then the tooth is usually the hardest to reach, I mean, relatively compared to the yoke. And the studies show that the 3-level, you have more savings actually on the tooth, which is a critical component in your thermal issues with the machine. And so not only will the 3-level inverter benefit the machines or power industries in terms of delivering high power quality, but actually it has advantages in terms of saving the core losses of your machines. So I think that's where the sort of the conclusions that came about this work. I'd like to acknowledge these are some of our funders, just NRF, Hydro-Quebec, and NSEC. Okay, thank you.